A popular image of great theorists is that they are deeply impractical people. The image is rooted in the perception that pure theory rarely comes to grip with messy reality. Of course, that perception is wrong. As science advances, we come to realize again and again how the theorists' abstract formulas accurately describe our most concrete reality. The psychologist Kurt Lewin expressed it well. Nothing is as practical as a good theory. Paul Milgrom and Robert Wilson go one step further. They are living proof that nobody can be more practical than a good theorist. It is the tradition of these lectures that they are given in alphabetical order. So our first speaker today is Paul Milgrom. After taking an undergraduate degree in mathematics in 1970, Milgram left university for a career as an actuary. Fortunately for us all, he returned back to university after 5 years in the insurance industry, earning a master's degree in statistics and a doctorate in business. His doctoral dissertation, which he defended in 1979 at Stanford University, revolutionized the theory of auctions. Throughout his distinguished career, first at Northwestern University, then at Yale, and for the last 30+ years back at Stanford University, where the voyage started, Paul Milgram has made a vast number of long-lasting contributions to the economic sciences. They range across the whole spectrum from pure game theory to finance and macroeconomics. But despite its dazzling diversity, Milgram's work always manages to shine a bright light on fundamental questions regarding the organization of economic activity. The one topic that he has always returned to, developed further, and made more applicable is that of his dissertation, the analysis of auctions. It is for this work that he receives the prize, and it's about this work that he will talk today.
Hello, everyone. It's great to be here today. It's especially a pleasure to have been awarded this prize with Robert Wilson, my PhD dissertation advisor. How exciting is that? And Bob's already given his talk, and I'm going to talk to you today about further aspects of the work. My talk is entitled Auction Theory Evolving, because as you'll see, we've continued to work on new aspects and ask new questions over a period of years ranging from my dissertation up to today. I have the subtitle Theory and Applications with an asterisk on theory because I'm a theorist. Most of the way that I learn about auctions or I study auctions is write models of them and prove mathematically that they have certain properties. Those are theorems. But in addition, I also sometimes have been engaged in experiments or sometimes in simulations where we simulate the results of different approaches to auctions to see how they might perform. And then finally, of course, there are the applications which have turned out to be quite enormous and involve very large sums of money. So, by the way, this picture that you see at the top here is a picture provided by the Nobel Foundation. It shows an auctioneer's hammer with math coming out of the hammer as two men lift the lid and show what's inside. So let's try to lift the lid a little bit today and see what's inside some of the auction models that we've developed. But before I begin that, I also want to thank the people who very early on in my career were major influences on my whole approach to studying these problems. Bob Wilson is the picture in the middle. David Krebs was also on my dissertation committee, and J. Michael Harrison, shown here. They were the key members of my dissertation committee at Stanford University. And then when I went to Northwestern to begin my career, the amazing young faculty that was there, Roger Meyerson, Bengt Holmstrom, and John Roberts were all there. John became my most frequent co-author. And Roger and Bengt, with whom I also worked, are themselves Nobel laureates. And these guys were quite an inspiration, and it's a real pleasure to be able to acknowledge them as I began this work. Now, the first thing that I did early in my career studying auctions was to try to integrate the insights that William Vickrey, another Nobel laureate, and Bob Wilson had in their approaches to studying auctions. Vickrey, who wrote the earliest auction models, imagined that bidders who attended an auction had some idea of what the thing was worth to them they were bidding for. They would have, for example, a maximum price of $100, and they would say, it's worth $100 to me. If it's a sealed bid auction, how much should I bid? If it's an English auction, what should my strategy be? And that was the approach that Vickrey took. And he also introduced using game theoretic methods and applying Nash equilibrium to study those questions. Wilson had a different model. Wilson was motivated, among other things, by the bidding for mineral rights, for example, bidding for oil that might be under the ground or under the ocean, and where those rights are being sold by the government. And the value of oil rights depends on how much oil is down there. It's roughly the same to all the bidders. It's not that bidders have different values, but they have different information about the values. And that different information leads to a problem that's called the winner's curse. The winner's curse is the problem that when I bid for something and I win, I'm more likely to win if I've overestimated the value than if I've underestimated it. So the bidders are not winning a random selection of based on their estimates. They tend to win more often when they've bid too high because they've overestimated value. And there was a great concern about how did auction design make that problem worse? How did different auctions affect the amount of revenue that might come from the whole process? And would the seller benefit by revealing information and protecting bidders somewhat from the winner's curse if the seller had any information to share? So Bob Weber, shown here, and I developed a model in which both private and common value elements could be at work at the same time. So something might be worth more to me. I might have a higher estimate of how much oil was under the ground. I might also have higher value for the oil under the ground because I had a greater need in my business. And a typical theorem, one of the theorems that we proved in our 1982 paper studying this is in the model that we created. If you studied Nash equilibrium, the expected price, the average price that would emerge from such an auction would be highest if you used an English ascending auction. It would be next if you used a Vickrey second price auction, and it would be lowest if you used a standard sealed tender, what economists often call a first price auction. And we also proved in that model that the Nash equilibrium expected price is higher when the seller shares relevant information than when he does not share that information. So we began to learn about the questions we were asking at the time. Do the auction rules matter, and how do they affect the efficiency of the auction? How do they affect the revenue that comes from the auction? Now, that was the first thing I had done, but as we began to get deeper into the subject, Nancy Stokey and I began talking. Nancy is a distinguished fellow of the American Economic Association, and she and I began talking about, well, what about trade like occurs in financial markets? What if there's common values, but there's concern on both sides? There's a buyer, there's a seller. The buyer's concerned he might pay too much. The seller is afraid that he's only going to buy when he's overestimated the value. The seller might be concerned that she's selling too cheap, He's only going to succeed in selling if she's underestimated the value. What would happen in a common value setting where both sides were worried about the winner's curse? And how would that depend on the rules that were used? Might different rules lead to different outcomes? And again, this what we decided to study was the simplest possible case, where the only difference between the buyer and the seller was the information they had about what was being transacted, and they didn't have any fundamental reason to have different values. And we proved what became a pretty well-known result called the no-trade theorem in 1982. If we had risk-averse buyers and sellers that had the same prior beliefs but different information, and if each of them rationally decided to participate in this mechanism and to accept whatever the proposed trade that emerged from, then regardless of the rules of the mechanism, the trade had to be the zero trade, which is to say that there is no way that a mechanism that both the buyer and the seller would agree to participate in based only on difference in information would lead to trade in this setting. That was pretty surprising at the time, because in financial markets we often thought about people trading based on differences in information. But this suggested that in order for there to be effective trade with people having differences in information, there had to be some other reason for trading as well. For example, somebody who's just had a deposit in their pension fund is buying securities for long-term investment, or somebody who wishes to make a down payment on a house is selling securities for a transactions reason. And if there were people like that trading, then people who had information could be trading at the same time. Now that raised the question of what would it look like in a financial market when we had both kinds of traders present. And Larry Gloston and I, still at Northwestern, began to work on that. Larry was a graduate student in the finance department at Northwestern. And we were talking about intermediated trade, the kind that we often see on securities markets, where there is somebody who makes a market, what we called a specialist, who would buy shares from whoever was, or securities from whoever was approaching to sell them, and would sell from people who were approaching to buy as people arrived over time to engage in transactions. And we imagined that some of these traders were trading for the private value reasons, such as I described, new investments in a pension fund or payment for a college education. And some were common value traders who were speculating, who thought they had superior information and were trying to make money on the trades. How would the market makers set these prices, and how would trade evolve? So, and if the market makers were competing, how would they set the prices? And how did the prices come to reflect information? Another big idea in finance at the time was the efficient markets hypothesis that Gene Fama was advancing, especially Gene and others, that suggested the idea that the prices would somehow efficiently combine all of the information that was available in society. Well, how did that information get to be in the prices if the traders were the ones who had it? And another idea that was present in the models of the time is that somehow or another my information would already be present in prices when I was trading on that information. How could that possibly be? If the specialist who's making the market doesn't know my information, how could my information possibly be in the prices before I engaged in trade? So Larry and I studied this and created a model in which a market maker quotes prices in competition with other market makers. And it turned out that in this model, the market makers would end up quoting two prices: a bid price, which was what they offered to buy shares that you might, or securities that you might sell to them, and an ask price, which is the price that they would demand if you were buying from them. And it always turned out that the ask price would be higher than the bid price, and these prices were conditional expectations. That is, the market maker would take into account, if I offer these prices and you buy from me, maybe you're buying from me for innocent reasons, but maybe you're buying from me because you have information that I've set the price too low. And I have to build in a little margin to cover the losses that I might suffer from that. And if you're selling to me, similarly, I have to build in a little margin. I have to offer a little less to cover the losses I'm going to suffer to the parties who are well informed. So the bid price and ask price would be pushed apart. And the transactions price at which trade actually took place would be the ask price if the trader who comes by is buying, and the bid price if the trader who came by was selling. And so we would get movement in the prices. The prices would reflect information. And notice that the price that you buy from, if you're buying from me, already reflects the fact that you want to buy from me. So your price does reflect something about your information. We were getting that feature as an endogenous feature of the model that we studied. And well, did this cause any trend in the prices? Would it be that prices would go up and up? Should we expect that? Or prices would go down and down depending on how people proceeded? Well, no. One of the main theorems of the Gloston and Milgram paper was that transactions prices and the associated public information form a martingale. That's a mathematical object, and it means roughly that there's no drift in the prices. When the prices step up, they tend to stay higher. They might fluctuate up or down around that, but they don't systematically come back down again or systematically continue to drift up. And this became a fairly standard and well-known model of trading in financial markets. Now, together with two more of my students, Marissa Beck and Nick Arnosti, I also studied what would happen in auctions and internet advertising. In the early days of the internet, many of the ads that appeared on websites were the same kind of things you saw in a newspaper. The local auto dealer has a sale this weekend and wants you to come in. But more and more, as we all know now, the so-called performance advertisers would try to select particular individuals. For example, they might decide that, notice that a particular person who's browsing to a website has a history of buying designer clothing, and they want to show designer clothing ads to that person. Now, this created a problem for the traditional display advertisers, because if you picked those people out and sold those ads separately, it might be that all the high-income people would be gone, and you'd be showing your car sales ad only to low-income people who weren't likely to show up at your dealership on the weekend. There'd be a problem, a winner's curse type problem, an adverse selection type problem. And we wondered whether there was a way to design auctions to inoculate against that problem. And that was the problem we studied, where now for each advertiser there was a common value, some attribute of the person that everybody cared about. For example, we all prefer to advertise to people with high incomes or people who are, for various reasons, responsive to advertising, but also a match value. Is that person a good match for me? If I'm selling designer clothing, or I'm selling vacation travel, or I'm selling automobiles, I want to be matched with people who have that need currently. Those are the people I want to advertise with. So we set up a model where the value was the product of those things. And we wondered, can we design an auction which protects the display advertisers against adverse selection, has a deterministic winner selection rule, it's a real auction design, it's strategy proof as the traditional auctions were at the time, the Vickrey-like second price auctions. It is efficient in terms of its allocation among performance advertisers, but it had two new properties. The property of being free of adverse selection for display advertisers so that they would be protected, and false name bidder proof, because on the internet it would be possible to design for a bidder to apply to bid under multiple names and try to manipulate the outcome by putting in multiple bids on an item. So if you wanted to protect against that and also protect the display advertiser against adverse selection, what could you do? And we showed that this set of auctions that satisfy this property could be characterized. It's a one-parameter family in which the performance advertiser wins if the ratio of the two highest performance advertiser bids exceeds some parameter alpha. And alpha could be varied, and that gives us a one-parameter family of auctions. These were the only auctions that had this property. It was a brand new auction design, was used for a little while until the internet advertising market has changed a lot over the years, and new problems needed to be solved. But this is a solution, gives an example of how you take a particular problem and approach it mathematically to understand what's possible and what can be achieved. Now I'm going to come to radio spectrum and invention. So this is an invention that Bob Wilson and I created for the Federal Communications Commission in 1993. We were both theorists at the time. I certainly had no practical experience, and I had thought that I had nothing to contribute, really, is what I thought. But Bob and I were asked by what was then Pacific Bell to look at a proposed auction that the Federal Communications Commission had. And Pacific Bell's problem was that they had a number of problems, but one of the problems that they faced at the time was that they wanted to acquire licenses covering Northern and Southern California. There were multiple different licenses that would do that, and they had to decide which ones to bid on. How could they make a decision like that? And how would they know which ones were cheapest, what the relative prices would look like? Along with Bob Wilson, Preston McAfee made a proposal very similar to ours. And the FCC adopted the Milgram-Wilson proposal, but it was pretty close to the McAfee proposal as well. And I'm showing here for the first time Evan Querelle, who was is an economist at the Federal Communications Commission, who both conceived of the whole idea of spectrum auctions in the United States and also helped guide this to success. That is, he helped not only promote our ideas, but make adjustments to them so that they were practical. He was concerned about the worst case performance and directed us to focus on attributes like that. Now, in deciding how to solve this problem, I had been influenced by my own participation in certain charity auctions. In charity auctions, for those of you who have attended them, one common thing is called a silent auction, where there's typically a room with tables and items are either sitting on the tables or descriptions of items are sitting on tables together with a bid sheet. And you as an individual might walk around and say, you know, that bottle of wine looks interesting. I'm going to make a bid on that bottle of wine. You write down your name and you write down a number. And this goes on for an hour or so before dinner at a charity event. And many things are for sale at the same time. That appealed to us as a model because with many things for sale at the same time, Pacific Bell would be able to decide which of these licenses it could afford, which was the best bargain, and bid accordingly. But there was a problem in the charity auctions, and the problem was something called bid sniping. For those of you who have ever attended one of these auctions, you will know that one thing that some bidders do who are trying to get real bargains for themselves is they'll say, yeah, I want that bottle of wine, but I'm not going to bid on it yet. This auction ends at 7 o'clock. I'm going to come back over here at 6:59 p.m. Before the price has been bid up, and then I'm very slowly going to write down my name and a price, and I'm going to win that item, and I'm going to win it without having to face competition from other bidders. So, and there's a lot of that goes on in these kinds of charity auctions. So that was bid sniping. We wondered whether we could adapt the rules of the charity auction, or I wondered whether we could adapt these rules to eliminate bid sniping. And so we created the simultaneous multiple round auction with what the FCC called the Milgram-Wilson activity rule. And the idea was we introduced a new rule that kept track of the bidding that was going on in the auction. And it meant that you would be unable to make bids late in the auction if you weren't also bidding early in the auction. You couldn't just engage in bid sniping. And in addition, the auction wouldn't end when, if a new bid was made in the last round. Whenever a new bid was made, there would always be an opportunity for somebody to come back and say, oh yeah, you bid 100, I want to bid 101. There would always be an opportunity to reply. So these were the two changes we made relative to what is in the charity auction. And it was judged a great success. It got wonderful press. The New York Times had an article calling this the greatest auction in history. And it got copied around the world. And hundreds of billions of dollars of radio spectrum licenses have been sold using this design that we created for the FCC in 1993. And yes, I wrote a theorem about this, that if the bidders bid straightforwardly, which is not what we expect, but if the bidders bid straightforwardly, this mechanism would lead to prices and allocations that converge to an approximate competitive equilibrium. So that is, the prices that would emerge would be at a reasonable level. The allocations that would emerge would be efficient. Now, yet another advance. I began thinking at this time, I was talking to Alvin Roth, another Nobel laureate who was at Harvard at the time, now my colleague at Stanford, who had been doing work on matching markets. And he had redesigned the National Resident Matching Program and was interested in designing organ exchanges and such. And these were mechanisms that didn't have money involved in them at all. And yet it felt somehow to us like there was some connection between what he was doing and what we were doing. So the puzzle was the mechanism that Gale and Shapley introduced for the so-called marriage problem, which was just matching with no money involved, has no role for prices. Is it connected somehow mathematically to Vickrey's price-based auction mechanism? You know, I think to most people who look at this from the outside, it would seem that there's no connection at all. They look very different. But there were some intriguing similarities. In both mechanisms, it turns out, it's a dominant strategy for bidders to make truthful offers, both in the Gale-Shapley mechanism and in Vickrey's mechanism. And in both mechanisms, if they make truthful offers, and if the offers are substitutes, then the outcome is what's called a core allocation, and it's a particular core allocation, the one that's most preferred by the bidders. It's just too much of a coincidence that those properties would be shared by these two very different looking mechanisms. So John and I, John Hatfield shown here, and John was a graduate student at Stanford at the time, introduced our model of matching with contracts. And in the matching with contracts model, offers are accompanied by terms. So for example, if a man makes a proposal to a woman in the Gale-Shapley model, he just says, "Will you marry me?" And in our model, he says, "Will you marry me and let's be graduate students at Stanford for the next 4 years?" Or he says, "Will you marry me and we'll go run my dad's store in Topeka, Kansas after we're married." And in our model, the woman could care not just about the man, but about the terms. And when those terms were allowed to be money, then what you have is an auction. And when those terms are trivial, that is, when the only thing you care about is the name of the person, that's the Gale-Shapley mechanism. But there's a whole class of mechanisms that's encompassed by this matching with contracts models, and all of them share these properties that are shown here. So we were able to show that these two mechanisms are both special cases of our matching with contracts mechanisms, and that all of these mechanisms share these properties. And these mechanisms, by the way, have been subsequently used to develop new kinds of market designs now that we understand how these properties can be generalized. Now, radio spectrum allocation is actually quite a bit more complicated than what I hinted early on. We were able to deal with simple cases where the licenses were substitutes for the bidders, but often real bidders have a problem of they have a business plan in mind, and they're trying to win a collection of licenses that allows them to implement that plan. For example, in the first auction, Pacific Bell wanted coverage in both Northern and Southern California to have a statewide plan. This was before the national plans that are obviously so prominent today. And sometimes bidders needed to achieve efficient scale. They needed to buy sufficient bandwidth in the licenses they acquired to make their plans viable. And the risk that they face in the traditional design is they might win some licenses that give them part of what they need for their businesses without being able to acquire the rest to actually have a viable plan. So the way that's handled in spectrum auctions is to allow bidders to bid for combinations of licenses. Now, there are lots of combinations, and figuring out which combinations to bid on, they need some guidance about what the prices will be. And Peter Crampton and Larry Ozabel, the top row here, worked with me to develop a method to help provide that information to bidders before the final round of bidding, in which they had to commit to the licenses they were trying to acquire. And Bob Day, shown in the at the bottom here, worked with me on the problem of finding a good price. That is, the first question was how do bidders identify and bid on relevant packages, and the second is what pricing rule creates the best incentives for the bidders to report their information truthfully, subject to ensuring that there is competitive revenue for the seller. The government gets a fair price for what it's selling. And Bob Day and I showed that an auction design minimizes the bidder's total incentives to bid untruthfully and provides competitive revenue from truthful bidding if and only if it's in a class that we identified of what's so-called minimum revenue course selecting auctions. So we identified the class of auctions that of pricing rules that would have this property. And again, this is used for real-life auction design. It's been used in many auctions, not in the US, but in Mexico and in Canada and the UK and Australia and around the world. Now, package bidding is a hard problem because there are so many packages a bidder can bid on. If you have an auction for 100 licenses, there are 2 to the power 100 different combinations that you can make from those. And that's way too many for anybody to bid on in practice. And so together with John Cagle, shown here, and Yen-Chen Lin, who was a student of mine, John's a professor at Ohio State University, we wondered, what can you do? Can we have a good outcome in this kind of circumstance? And we showed that if bidders bid to up to their limits on relevant packages, then you can get good outcomes. You can get efficient allocations or core allocations that emerge from this bidding. And we also showed that you could use simulations with auto bidders to predict how bidders would bid to see whether relevant packages could emerge from different auction designs. Now, the biggest of our challenges was the recent incentive auction, the broadcast incentive auction. The concept for this was Evan Querell and John Williams created this. And the idea was that to buy TV broadcasters' rights from some TV broadcasters, to repack the others into a smaller set of channels, and then to sell to create television to create mobile broadband licenses out of what remains and sell those to mobile broadband companies. And this is a particularly hard problem because deciding whether you can assign TV broadcast channels to broadcasters without creating interference is what's called an NP-hard problem. It's a problem that's hard even for computers. And I led a team from my company, Auctionomics, with Ilya Segal, my colleague at Stanford Economics Department, and Kevin Leighton Brown, computer scientist at the University of British Columbia. We created new algorithms, especially Kevin created new algorithms to do a better job of approximating the solution to this problem. And Ilya and I created a class of new auction designs that became it was a class of new auction designs that actually accommodated computational limits on computers while still providing the kinds of good properties, strategy proofness, budget compliance, privacy preservation that were desired from auction designs generally. Now, I have a lot more going on. I've got a bunch of co-authors on working papers currently in progress. On the first column here, you see Mohammed Akbarpour, Shengbu Li, Scott Commoners, with whom I'm working on investment incentives in auction problems, Martin Bickler and Gregor Schwartz, Josh Molnar, Neil Newman, Mitch Watt, with whom I'm working on a series of other problems that are all related to auction design or to the underlying game theory that helps us analyze the auction design. And besides these guys, I'm really proud of the newest group of students that are coming along that I know are going to have a major impact. And you may see a gender difference in this group too. A lot more women involved now in this. You see Agat and Pearl and Evan in the top row, and you see Ziyang and Lucas and Kevin in the bottom row. These are all tremendous students who are going to have a big impact on the future of auction and market design. I'm very pleased to welcome them to the group, and I hope you will join me in doing that.
Robert Wilson's academic path has been remarkably straight. He earned a bachelor's degree in 1959, a master's degree in 1961, and a doctoral degree in 1963. All three degrees are from Harvard University. The last two are in business administration. The year after completing his doctoral degree, Wilson accepted a position at Stanford University's Graduate School of Business, where he has now served for 56 years. All this time, Wilson has tirelessly been making management more scientific. Economists early understood how to take optimization theory to production and logistics. Wilson's genius was to realize how a new branch of applied mathematics called game theory allowed similar methods to be used under circumstances involving real people with personal desires and private information. He became the world's leading expert on pricing in general and on auctions in particular. He showed us that it was possible to prove theorems in the morning and change business practices in the afternoon. During the half-century that has passed since Robert Wilson wrote his first academic article on auctions, the field has developed from a theoretical curiosity to one of our most practical pieces of economic knowledge.
I'm Robert Wilson. This year, with Paul Milgram, I'm sharing in the Nobel Memorial Prize in Economics. The citation was for advances in auction theory and invention of new auction formats. Because of that focus, I will be talking today about my work on auctions, which is a portion of my broader work in economic theory. I will be giving some examples of auctions, but also drawing broader conclusions about the implications for economic theory. I'll begin with intellectual history before I present the main motivating examples that were also the focus of the work cited in the committee's citation. So the title of my talk is Strategic Analysis of Auction Markets. I'm going to begin with a brief history of the intellectual developments within economics. So starting from the bottom and working up to the present time, I've emphasized a sequence of key events. Before I describe those, let me first emphasize that this set of developments in economic theory had a parallel in terms of the development of game theory, which later these two sources merged together in a unified framework. There was also an intermediate period in which also within economics there was the flourishing of general equilibrium theory, but I'm not going to talk much about that today. So in this representation, I emphasize as a departure point the 1945 work by Hayek on markets as information systems, in the sense that prices in effect guide private decisions. These are public prices that are signals that are seen by all the private individuals that are influenced by them. Somewhat missing in that description is how it is all of this private information that's held by individuals gets embodied in prices. At the next level, in 1970, we saw a severe critique of this point of view in economics. We had a series of articles showing that the effects of informational effects of such features as adverse selection, screening, and signaling could strongly affect market performance and affect efficiency. At the next level, in 1973, we saw a new departure in economics, led by Leo Hurwitz, which we now have come to call mechanism design theory. It treats markets as eliciting information, which is then used to allocate resources. At the next level, we have some applications, very practical kinds. There was an intervening period where we sort of applied the theory, but in 1994, Paul Milgram and I participated in the design of spectrum auctions, and in almost the same time, Alvin Roth, who received the Nobel Prize 8 years ago, had done very key work on matching markets, along with using work from Lloyd Shapley of an earlier period. And that brings us to the present, where nowadays market design, sometimes called economic engineering, is seen as a major subfield of economics, in which actively seeks to improve market procedures and establish new trading platforms. So I'll be going over this brief history as in effect, the motivating source, the fountain from which my work was drawn. I had been interested in the informational content of prices. I was interested in the role of private information and how what the price formation mechanisms were. Because there's so many different kinds of markets. There are auction markets, specialist markets, double auctions, all kinds of various kinds of trading platforms, of course. So what I sought was a more detailed analysis of these features, and to approach that subject, I was motivated by this development that we see here. So we're going to study first markets as information systems. That starts with Friedrich von Hayek's work in 1945, in which he interprets the market as eliciting bids, in effect, to find out what the willingness to pay or supply is from demanders and suppliers, to find a feasible allocation and prices that will clear the market. Those prices are then seen as a guide to private consumption and production. All of this was upset in the 1970s, even though there had been this intervening period in which general equilibrium theory had advanced greatly. It was now a general way of characterizing economic equilibrium in a general system as kind of a big fixed point in prices. Prices were such that demand equals supply. But in the work of these four authors, James Mirrlees, George Akerlof, Mike Spence, and Joe Stiglitz, as well as some of their co-authors, what we've seen is a severe critique of that body of theory. Some of that was you might think of as sort of mild amendments, in the sense of Mirrlees using ideas of screening and design of optimal taxation. But we saw with the Akerlof's model of a lemons market the severe effects of adverse selection, which could lead to the collapse of a market, or severe, in general, it's severe inefficiency. In the job market signaling by Spence, what we're seeing is a kind of inefficiency. All of this is associated with the general notion of rational expectations. To what extent do prices convey information? Are they a sufficient representation or aggregation or sufficient statistic for the information that's dispersed in the economy among all the agents, among the participants? So what we've seen from these developments was that the allocative efficiency of markets depends critically on informational efficiency. The prices must be representing, for For example, in the case of the Akerlof's lemon market, they're not prices that are distinguishing the different qualities of the products that are on the market. So this is an incomplete market. The prices are not adequate to fully describe the informational content of the participants in the market, in this case, the suppliers. So from that, we see that private information strongly affects incentives. So this is something that had motivated me since even the 1960s. So I'll now be talking about how that emphasis, that focus on market microstructure that I had from even the 1960s, having, by the way, read William Vickrey's work on auctions, which is part of which is for his Nobel Prize was about. So the principal development that I'll emphasize is by Leo Hurwitz in 1973. He emphasized that markets are games, that agents are acting strategically. So this is a representation of a market not as a fixed point in prices, but as a fixed point in strategies. It's a whole different conceptualization of how we should look at markets. The key idea is that people in the market have various kinds of information. This goes, I have represented here as an arrow, that somehow agents acquire information. That information guides the bids and offers that they make. Those bids and offers arrive in the market. The market has a way of translating bids and offers into prices and an allocation that is the outcome. So this is, interprets the market rules as affecting ultimately what this agent's strategies are, because ultimately they see that those rules at the end are going to affect how their bids and offers are translated into an allocation and prices. So earlier on, it's going to affect their strategies. And this is what determines the allocative efficiency of the market outcome. In this representation, characterizing prices as just demand equals supply is insufficient. We already saw that in Akerlof's result, where demand equals supply, but at zero prices and zero transactions, which is an inefficient outcome. So the market microstructure is really crucial here. You need to understand what the prices are representing, how the prices are formed, how agents can behave strategically in influencing what the outcome will be through their actions, but I'm using in general bids and offers as a representation of their actions, which may in fact be much more complicated. So from this point of view, market design is about designing the game that's played by the agents. It's a way of translating the actions they take into outcomes. This was the beginning of the infusion of game theory into economics. I emphasized earlier on that there was a parallel development of game theory. It was treated in many ways like a subject in applied mathematics, but in fact its origins lay with von Neumann, and the von Neumann-Morgenstern book was about games and economic behavior. It had been preceding and had a substantial and persuasive literature, but this is really at the point at which the sort of merger came, because in a sense, the economic market microstructure was really being translated into the terminology of game theory, and it was the techniques of game theory that then became the tools of analysis in the later work. So from the point of view of market design, this is really a saying that game theory provides a tool for engineering the game in the sense of the active sense, and it predicts how market structure affects outcome, and it has the key, from the point of view of economics, the key focus is on agents, information, and incentives. So I'm not going to talk about this game theoretic perspective, just to sort of make clear what it is we're talking about. So in a game, the key feature is an explicit characterization of who knows what, when they take actions. So it's who knows what and when. This is what a game is supposed to specify, and it specifies it in rather fine detail. So it's not a question of just a macro representation, demand equals supply. Instead, it's at the more micro level of how bids and offers are made, how, say, a market operator translates those behaviors into outcomes. So the market is seen as eliciting agents' information via their bids and offers. The agent's strategy is to convert their private information into these actions in the market. And then the outcome, given by the market procedures, converts all the agent's actions into an allocation. From the agent's point of view, the market is itself a game because the outcome depends on not only that individual's strategy, but all strategies. We see it as a game of incomplete information because the participants have their own private information about their preferences or technology or whatever. The market design is taking account of the agent's information and incentives in putting together the rules, the procedural rules for running a market. Those rules, in effect, define agents' feasible strategies and ultimately then their incentives. So from this perspective, we can approach the most straightforward and familiar market mechanism, which is an auction. But rather than talk about a simple auction, I'm going to talk one that has a complicating feature, which is that there's a common value. And my work on this back in the 1960s was motivated by working with the Department of Interior on oil leasing, that is, leasing of rights to explore for oil over a certain tract. And in that case, there's a common value, which is namely there's some amount of oil under the ground, possibly zero, but it cannot be observed directly. There can only be indirect estimates of what that is. For all the bidders, their preferences, their willingness to pay depends upon how much oil there is, whether there is oil, how much it is, how much it would cost to extract it, what future prices of the extracted oil will be. All of these common features affect all of the participating bidders in the auctions of oil leases. So, in this case, we interpret this as saying that the bidders obtain unbiased estimates of the value of an item because they undertake surveys of various kinds to try to estimate how much oil would be under the ground. These are called gravimetric surveys, seismic surveys, and so on. As they higher estimates, generally under some circumstances, higher estimates lead to higher bids. The item is sold to the highest bidder at the price of his bid in that auction design. And the outcome is then that the bidder with the highest estimate wins the item. Well, this is sometimes called the winner's curse. It reveals ex post that that winner's estimate was actually biased, or at least biased relative to the estimates obtained by the other bidders. Now, optimal strategies, we're going to anticipate and correct for this adverse selection. The fact that all of the bidders are having imperfect estimates and the winning bidder is likely to have the highest estimate. All of this has to be corrected for. It's really more of a statistical problem, but it can be done. And then you see that the auction price will partially aggregate the bidder's information. And with many bidders, the highest bid, I say here, probably close to the actual value, but you could say that it converges in probability. Okay, now let's talk about a more complicated example, one of the ones that was cited by the Price Committee, and it's the auction of spectrum licenses. So this is the next level of complication. So in this case, the bidders have imperfect estimates of the spectrum license values because they have imperfect estimates of what the demand for, let's say, cell phone service will be. So there's a common factor, namely consumers' interest in using cell phones. So the communication firms that are going to be selling cell phone services are very interested in what that common thing is. To what extent will consumers be interested? And even since nowadays market penetration is about 100%, it's interesting that back then they thought that the market penetration maybe might reach as high as 30%. So that's the extreme case of adverse selection. So the new complication is that the bidders were seeking packages of licenses in order to get spatial coverage. The ones that say Northern and Southern California represent complements, whereas 2 licenses in Southern California would be substitutes. In this case, a ascending auction allows them to get better and better information during the process by inferring from others' bids, estimates of this common value, and that improves allocative efficiency. But when they're looking for packages of licenses, it's good to have a simultaneous ascending auctions, simultaneous for all of the licenses simultaneously, to enable the bidders to assemble the packages they want. There are complications. There are advantages. Let me mention those first, which is near the end, the bidders are in effect choosing at the prevailing prices which items, which licenses they want to have, what they would like to pick to be their package at those prices. But this is somewhat impaired by further need, which is an activity rule. This is particularly a remarkable development by Paul Milgram. It's to ensure that the bidders are actively reflecting in their bids what their true preferences are, and they're not maneuvering. So an activity rule is in effect a requirement that the bids must be consistent with revealed preference, that they have some preference over packages that is for which their bids are consistent. There is this exposure problem that's a deficiency of this auction design, because a bidder could get only part of a package, wins Southern California at a very high price, does not win Northern California, and then without Northern California thinks that it paid too much for Southern California. So, and there are other possibilities, all of which has to be addressed in the fine details of the market design. And in some ways, a market design of this kind is limited in what it can prevent. So the most complex system of markets, auction markets that I worked on, are auctions of electricity. I'm going to describe that somewhat summarily. In these cases, there's a whole system of auctions that are going on, because there are auctions for energy, for transmission, for reserves, and moreover, there are forward markets and spot markets. Prices are very diverse. At any one time, there are prices established at every node in the transmission network. So this is a very complex set of auctions that have to be integrated together. The usual way is that it is run by the system operator, who conducts a market simultaneously for energy and transmission. There are auxiliary markets that are run for reserves, and then the hedging markets that are privately run, not by the system operator, but these are private markets. They then can settle at the prices established in the system operator's spot markets. So, as I mentioned, there are all these complications. In electricity, there's typically like a day-ahead market, an hour-ahead market, the spot market, which is like every 5 minutes. In addition, you can have people who are bidding with genuine supplies that are being offered in the market, and some are just are financial traders. They are speculating. There are the auxiliary markets for reserve capacity have to be differentiated by quality. That is, how long they're available, when they're available, how fast can they ramp up. So I emphasize that this is a very complex system, and the market design is genuinely an engineering activity, because you have to take account of the system integration, making sure all of these coordinated parts, all of these parts work in a coordinated way. I emphasize at the bottom here in this slide that there's a modern dilemma, which is how to cope with the variable supplies from wind and solar sources. Well, that in fact is an example of a market design in the sense of creating new markets, forward markets for demand curtailment, or an alternative version is priority service. So let me conclude now with some summary points that for imperfectly competitive markets with private information, which are the kind that I've addressed here, game theory is this very useful tool for studying the market microstructure. It enables the analysis of information, incentives, strategies, and the effects of the market rules. You can build into it effects of intermediaries, the market operators. All of these can be included, and you can address the effects of regulatory policies. From an empirical point of view, it's important, it provides a structural model for empirical studies, econometric studies, and for public policy. I've emphasized in these remarks today that it's also a tool for improving markets and designing new markets. The engineering approach is to focus on the fine details, use game theoretic thinking, not necessarily exact representation, but a fairly close adherence to capturing the actual details of the market operation. The progress I emphasize from my own experience depends on really deep knowledge of the industry you're dealing with and how its markets function, because every one of the industries I've been involved with operates differently. They have different concerns, different technologies, and so on. So I don't think of market design as being something that one just goes willy-nilly to do. You have to really understand the industry you're dealing with. And that, of course, ultimately devolves into the incentives that must be well understood. So let me conclude now, make a sort of a few summary remarks. I've tried to emphasize that from the very earliest part of my work in the 1960s, I was interested in price formation, private information, the details of how prices get formed in these markets and who's running the markets and how they conduct their operations. This turned out to fit in very well with these developments in economic theory. There was this parallel development of game theory. It provided the tools for that kind of analysis, and it's now become an integral and an important part of economic theory. If you look at the journal articles today, about half of them use game theory in a direct and constructive way. PhD students in economics nowadays, at least if they're going to do economic theory, they need to understand that literature, they need to understand these techniques. Even for empirical work, the good structural models are ones that are based upon a game theoretic foundation so that they capture enough of the details. There's not just some linear regression, it's rather a more structural representation of what goes on. So I see my work as just fitting into the work of a whole cadre, a large group of fellow theorists and practitioners who've worked over, actually, for my work's gone on for nearly 60 years. And over that time, you've seen a steady development of this line of work. It's not only had its theoretical successes, it's had these practical accomplishments. And the citation by the committee of the work on auction improvements in auction, market design, auction design, and so on, which is also acknowledged in the Nobel Prize to Alvin Roth in 2008, 2012, 8 years ago. So that market design has become this subfield of economics, and I think for me, I see this as a good thing with a lot of promise and prospects for the future. Thank you.